Okay, so pleased to introduce Ewelina Zatorska. She's going to talk to us today about the dissipative Aw-Rascle system. Thanks, and floor is yours.
Good evening, everyone. This is evening for me, so I'll try to make it a calm evening talk for everybody. So I'm at the moment in London, and it's already dark, as you can see here. And I'm somehow sitting in an empty room, so please and interrupt me if you feel like I'm talking too much to myself. That's the feeling I always have when I give a Zoom talk. Thank you for inviting me. What I want to present today is actually a couple of results and that we worked on over the last year and a half, I'd say, together with a group of my collaborators and friends. So I would like to acknowledge Nilasis Chanduri, who is a postdoc in my group, Piotr Jazda from University of Warsaw, Edward Pajrazl from Czech Academia of Science, Laurent Navier and Charlotte Perrin from France, Strasbourg and Marseille. So let me go to the dissipative Aw-Rascle system. So for those of you who, it looks like, okay, I can switch the slides now. So let's focus first a little bit on understanding what the model really is. For those of you who work with the traffic equations, the word dissipative might be a bit mysterious or a little bit unusual in this context. So let me explain what I mean by that, what I mean by the model. So if we talk about one main traffic equations, sort of resurrection of the second order models, so the models that are using two conservation laws to describe one lane traffic, was announced in the paper, first paper of Aw-Rascle on the subject, and hence the name of the model. And it's a system of two PDEs that are written here. Those PDEs, however, can be derived from the so-called follow the leader system of ordinary differential equations, which basically describe dynamic of each individual, so position of each individual in the group and acceleration of each individual in the group via the system of ordinary differential equations. The important assumption here in this model is that there is indeed a leader, so the person, the driver of the vehicle just in front of the car that I'm sitting in, and I adjust my reactions. I slow down or accelerate depending on the velocity, on the behavior really of this car ahead of me. So if you go through some mean field limit kind of argument, you end up with the following two equations. So the first equation is just conservation of mass. Rho denotes the density, and U denotes the actual velocity of motion. So that's quite standard equation in the fluid community, and I will be referring to these analogies quite a lot here. Second equation is another conservation equation. It's a momentum equation, linear momentum equation. But in this system, the momentum is associated not actually with the actual velocity of motion u, but with the so-called desired velocity w. All right, so there is one extra unknown in the system, and therefore I have to close it by imposing some relation between w and u. And I say that they differ by the velocity offset that I denote by capital P of rho. So this is offset function, sometimes also called cost function of the motion. And it's the letter P here is not an accident. It plays a similar role to what pressure in the fluid equation is. It even was used for the first time as rho to power gamma, so the famous adiabatic rho that we find in the fluids. but it doesn't have to be like that at all. The rule to remember is that the actual velocity of motion is smaller than the desired velocity w by this offset, by this cost function. So that's what happens in a one-dimensional case. And already here, as I said, there is some problem. So the problem that was identified by this group of people and actually remedied already in the paper from 2008 is that this offset function, rho to power gamma, does not preserve maximal density constraint. So we can start from some initial density that is between 0, so let's say density is not negative, and some maximal packing density, we call it rho star here. So this rho star corresponds to the situation when the cars are bumper to bumper really. So the physical dimensions of the car, they prevent them from achieving densities that are above that. And the Aw-Rascle system that I showed you on the previous slide can violate this condition. So at some point, density could develop to values that are larger than rho star. And now the way to remedy this is actually include the offset function or cost function that blows up when density reaches this constraint rho star from below. So this is a function p epsilon of rho written here. And another important feature that was discussed in this paper is that actually this kind of sensing between the cars shouldn't happen everywhere with the same rate. So the authors advocated actually that that's an effect that should be negligible when density is far away from the congestion, and only shortly after the congestion constraint is met should the car sense each other with great intensity. So this function, they also considered the limit when this parameter epsilon goes to 0, creating this function, creating some sort of delta behavior here. So instead of having like a steeper and steeper singularity, we actually expect in the limit epsilon going to 0 to work with something that is referred to in the literature as hard congestion system. So a system in which the interaction appears only locally when rho is equal to rho star. So this hard congestion system is approximated by soft congestion system with this approximation of the cost function. And it's a part of my talk that I will touch upon at the end, towards the end of the lecture today. So we explained a little bit the situation in one-dimensional case. And my point to make now is that this is not the end of the problems with the system. So all of that was introduced was actually one-dimensional system for one-lane traffic. But now the question obviously is, what if we would like to apply this model, use this model in the context when we have a couple of lanes and possible vehicles that can overtake each other. So first of all, we would like to come up with the macroscopic model. The macroscopic model is the area in which we feel well because we can do some analysis, and it's of course much more efficient numerically than the microscopic model. So the underlying idea that I would like to sell here is that the system, the multidimensional system, should have the same sort of fundamental reasoning behind it, meaning that we have two conservation laws. First is conservation of mass, and second is conservation of momentum associated with this velocity w, right? So that's basically the idea that we would like to deduce again from the follow the leader model. Unfortunately, it is not so easy to do it, to derive this system even formally, because in multidimensional cases, in multidimensional traffic, it is not really so clear who the leader should be. So for example, if I was driving this car and if I was to overtake the car ahead of me, it is not true that I would only watch the reactions of the driver ahead of me. I could actually look around And in some cases, I don't know how about you, but I would definitely use my back mirrors in order to see the situation behind me somewhere here. All right. So there are a couple of modeling approaches developed for this dynamics, and I'm going to mention roughly two of most important ones. But if you perform the simple generalization here, the striking fact is that if you want to supplement the system with closing relation, you would have to compare two vectors with a scalar. So the offset function would be scalar still, right? So there is this dimension incompatibility between the quantities in the system. So what to do with that? Well, as I mentioned, there are a couple of modeling approaches developed already. So first of all, I would like to mention a paper of Harty, Mutari, and Visconti from 2018, where they simply looked at the offset function as a vector of two scalar offset functions. Both of them, they could be even singular functions, like in the paper of de Gondt and co-authors. So some singular functions with maybe some maximal packing constraint here. However, this does not include the situation really in which we actually look behind or look with various intensities to the neighbors around us. And for that reason, de Gondt and Andrea Tosin have proposed to work on the offset function, which is actually gradient of some scalar function P of rho. Okay, so now I compare two vector fields with the vector field, which is gradient of some function of the density. So we are closer and closer to explain the source of dissipation in my Aw-Rascle traffic equations, because this form of offset function will indeed lead to some dissipation in the model, and I'm going to explain it a little bit in this slide. So all of this story was in order to explain you that Aw-Rascle model could make sense in multidimensional setting, but in order to understand the dissipation in this model, let us actually come back to one-dimensional setting again. So my offset function will be a gradient or the partial derivative of some scalar function P of rho. And I will again link this P of rho to another function of the density denoted by lambda of rho. And this is quite, this is in order to rewrite my system in a way which I hope is familiar for people in this audience working on the so-called degenerate Navier-Stokes equations. So if I come back to Aw-Rascle model with offset function in the form of the gradient, and I express the second equation, the momentum equation, in terms of the actual velocity of motion u, I end up with this sort of pressureless, compressible Navier-Stokes equations. And I use the word degenerate to describe the fact that the viscosity coefficient in such equations, lambda of rho, depends on the density in such a way, actually, that this coefficient will vanish when density is equal to 0. Okay, so there is no pressure in this equation. There is also only transport and the dissipation term. Well, this is a situation in one-dimensional case. In multidimensional case, if I were to write something like that, situation is not that easy, because in multidimensional case, we of course have a difference between divergence and the gradient of the function. But if you were to do something like that, there is a second order term in the momentum equation. The problem is that it's not full dissipation as we would expect it for Navier-Stokes equations. It's only something that I would say the bulk viscosity in these equations. And then there is a bunch of lower order terms in terms of gradient of some function of the density q and velocity u, which can be written in the form of commutator. So this is just like a side remark that I want to present here, because we actually don't have that much of results for a multidimensional system in which we would be able to actually exploit this form of commutator on the right-hand side properly. So that's the introduction, explaining you a little bit of where we are, especially if you come from fluid equation community. It is important for you to place this kind of dissipative Aw-Rascle system somewhere between compressible Euler and compressible Navier-Stokes equations, both of them pressureless. So in fact, what I'm trying to do here is to find out how much of the results that we know are available or not available for one of those systems translates into something in between. So the Aw-Rascle system with this dissipation effect. I'll start first from the existence results for the Aw-Rascle system with dissipation in the multidimensional setting. And here the title reveals already that we are going to talk about a very weak notion of the solution, the so-called measured valued solutions. Solutions will be actually defined in the sense of Young measures. So let me explain a little bit why this is the case. So you've already seen two equivalent formulations of the Aw-Rascle system, one in terms of velocity W and the other one in terms of velocity U. I'm going to switch to another equivalent formulation of the system. Equivalent, of course, as long as we operate within the notion of classical solution. For weak solutions or for even weaker solutions, this doesn't have to be the case. So what I do right now is I rewrite the momentum equation so that I can get rid of U completely. Okay, so this is the relationship that I use. And if I plug it in to the momentum equation, I have two nonlinear terms in the momentum equation. First is the classical advection term, and the other is a nonlinearity that involves actually this kind of square root of the kinetic energy and gradient of some function of the density, which is related to our original offset function. Now, what happens if I plug for U W minus gradient of P in the continuity equation? You see that it changes into some kind of porous medium equation with advection term. So, well, it might be porous medium equation or fast diffusion equation, depending on the form of the function Q. But in fact, we actually expect some regularizing effect, some sort of parabolic regularizing effect that will come to the solutions of our problem through this, this kind of second order regularizing term in the continuity equation. All right, so this system has a natural energy structure, and this energy actually consists of two parts. First of them is the standard kinetic energy associated with the velocity W and with the velocity U, so actually you can perform the kinetic energy for both of these equations. Sorry, this is just equation written in W, and equation written in terms of U was on the previous slide. But if I multiply this equation by W, integrate by parts, something like rho times W to power 2 will be bounded in L infinity L1. So that's the first part of the energy. The second part of the energy is some sort of potential energy. So again, I look for some analogy to fluids, but this time, this part of potential energy doesn't come from the pressure because there is no pressure in the system. It comes rather from the structure, this porous medium structure of the continuity equation. So basically, what happens here is that I multiply this equation by P prime of rho, and I integrate with respect to omega. I denote the integral that appears here capital E. And because this term has a good sign, I will get some gradient estimates of some function of the density, let's say gradient of Q, coming from that term. All right, so if I summarize the a priori estimates, they look like that. So first, two estimates come from the kind of energy structure, and the second estimate, L2W12 estimate, comes from this porous medium term in the potential energy part. So this is the list of my a priori estimates, and I'm giving it here in order to explain a little bit a need of particular form of weak solution that I'm going to focus on going forward. So first of all, if you look at these estimates, you quickly notice that there is like a bit of imbalance in the estimates because we have relatively high information on row n, actually very strong information because the gradient is bounded. And if you come to the continuity equation, you can even bound the time derivative of the density in some negative Sobolev space. But there is actually no uniform estimate for the velocity W or for any equivalent of velocity. So by that, I mean, neither W is estimated nor U. So now if you imagine the situation that you would be working on some sort of weak compactness argument for this system, meaning that assume that I constructed sequences of solutions approximating, sorry, let me go back to the previous slide, approximating a solution to the dissipative Aw-Rascle system. The sequences are denoted by rho n, wn. With these estimates at hand, it would be difficult, or at least I don't know how to do it, to prove that the limits of those sequences will satisfy the equations in the weak sense. And why is that? Well, if we look at the continuity equation, the situation here is not yet so tragic. So even though not every quantity makes sense, so I cannot really talk about Wn on its own, I can always split rho n and that appears in front of it into two square roots and treat maybe square root of rho n times Wn as my first unknown, okay? So this would make sense. The whole term is integrable in some LP with p larger than 1. So there would be still a chance, maybe through some compactness argument, to prove that the limit in this term converges to something it should be converging. Likewise, because of relatively strong information about the density, the nonlinear terms with respect to density and even the gradients of some nonlinear functions of the density should not be the problem. We can maybe integrate by parts twice in this term. The problem appears if we look at the momentum equation, because not only it involves composition of two terms for which I have only LP estimates, but also the convective term is only L1 integrable with respect to space. So what it means is that by taking some uniformly bounded sequences in this space, L infinity, L1, and letting n to infinity, I may actually jump out of my space of Sobolev functions or Lebesgue functions and end up in measures. So in fact, there are two effects that can happen here in combination of two weakly converging sequences. We may have like oscillations here and oscillations here, but we may also end up with something that creates concentrations, right, as a limit of uniformly bounded L1 functions. And the same again happens in the other term that is associated with the gradient of some function of the density. So by this, I hope I convince you that the language of weak solutions might be too restrictive if we were to think about existence of solutions globally in time without any restriction on the size of initial data. And this is what I would like to cover with my first existence result. And for that, I will introduce the notion of the Young measures. So Young measure is actually a measurable map from a subspace of Rk. So to every point from some set Q belonging to Rk, I associate a probability measure. And this mapping of associating to Z a probability measure anchored in this point Z is actually Borel measurable for every test function from C0 Rn. So G is just our test function, and Xi is something that we sometimes call a dummy variable. And it only indicates that we integrate with respect to this measure nu z over the space for Xi. So Xi is an element from Rn. Now, this is the duality between the measure and the function. And I'm going to explain why it's already written in such a way that you'll see that this kind of object is suited to work with the nonlinear terms in the systems of conservation laws. So there's one particular example of a Young measure that I wanted to maybe discuss for you a little bit. Every sequence of measurable functions actually generates such measure. So it's enough to take for every point z a Dirac delta, which is centered at un of z. Of course, this is a probability measure. It integrates in to 1, right? But if we now consider the convergence of the sequence un in the natural topology of the weakly star converging functions in L infinity, we see that this un, again, this is maybe a little bit of abuse of notation, un understood as measures, probability measures of this form, they will converge to something that I denote by capital nu here. And this object here is called a Young measure generated by sequence un. And the convergence, of course, is in this weak star sense on L infinity Q for every test function, again, G on C0 Rn, right? So this object here, the limit of my sequence, is something that I will see as a limiting object of any approximation that I will come up with in order to prove the existence of solutions to my Aw-Rascle system. So one more remark about the Young measures and the definition, the general definition, before I come to specifics, is that this definition, this object is actually introduced to help us identify the limit in the nonlinear terms. So now let's go a little bit further with our hypothetical sequence un. If un is only bounded in L1, uniformly bounded in L1, but I know that there is some continuous function of un bounded in LP for some p larger than 1, then of course I cannot identify the limit of b of un as b of u, where u is a limit of my sequence un, right? Because precisely of what I commented on, I may end up in the measure. But I can use a Young measure generated by my sequence un in order to identify this limit. And this is again identified through duality between the measure and the function. And all of that is done weakly in LP prime, where P prime is a dual to this LP on Q, all right? So this is a sense that we will give to all limits of all nonlinear terms, provided that we have this a priori uniform bounds in LP for some p larger than 1 in our system. But unfortunately, Young measures, at least in their first, let's say, iteration, are only suited to capture the limits of the oscillations. They don't deal well with the other effect of weakly converging sequences, which is the effect of concentrations. So if it happens that for this nonlinear function b of un we have only uniform L1 bound, then I will still, of course, pass to the limit. I will denote this limit by bar b of u, which doesn't, it's nothing else by just a notation, a symbol. This might be a measure. Usually it will be some non-negative measure in my case. And I denote something that is called the defect measure, which is just a difference between this object, which is a measure, and the object that would identify the limit, the nonlinear limit, if I could. So application of my Young measure to this nonlinearity for some dummy variable psi. So in that case, I can say, all right, I probably can still approximate my nonlinearity by this identification that I used before, up to some mistake, some order, which I called defect measure. It is associated with the nonlinearity B. And if I am able to actually say that this defect is equal to 0, then it means that my limit can be identified with the action of the Young measure. All right, so let us see how this definition works in practice. I think it's absolutely horrible slide, and I hope that I'm able to explain it better than just you would be able to do by reading it. The important thing and the starting point for us really is to, or the way I was thinking about this problem when I was trying to solve it, was to go as safe as possible. So imagine that there is a problem with passing to the limit in the system in absolutely every nonlinear term. So in the momentum equation, you saw that the nasty nonlinearities were produced by the square root of the kinetic energy, but also by some gradient of some function of the density. A priori, I don't know what rho n generates, so I also included into my sequence that will generate a Young measure. And now this Young measure is going to operate on the phase space, which is just a space of values associated to the sequences. My dummy variables now are denoted by these tildes. So these are the variables for which I am going to substitute and integrate over them in my pairing here. It happens that actually this first sequence can immediately disappear from my definition of the Young measure. What this two lines here express is that whenever I have a multiplication by density, or maybe some function of the density, be it a square root or maybe q, I can basically jump to the Young measure or out of the Young measure formulation with the function of the density. So density can be identified immediately from the a priori estimates. The way we do it at the level of the measure itself is that we write that the measure splits into the atomic measure, so this one centered on our solution, limiting solution, times a Young measure generated only by the sequences. Right, so this is the way we actually write to say that whatever approximates density converges to the limit rho strongly, right? And if we were able to identify this Young measure with a product of deltas centered at the dummy variables associated to this sequence or that sequence, then we would actually say that we have strong convergence of all sequences and a proper weak solution to our problem, all right? So there will be convergence to a point to a weak solution of my system, but it will be a strong convergence for each of them. All right, so with this definition of Young measure, the weak formulation of the continuity equation and momentum equation, they just use this kind of duality formulation between the measure and the nonlinearity involving the sequences. The thing maybe I would like to notice is that we have a couple of these defects of measures associated with the nonlinearities. So first of them appears already in the momentum equation. It's denoted Rm, and it is associated to both of the nonlinearities, the one coming from kinetic energy, and the one due to the product of this square root of kinetic energy and gradient of some function of the density. So that's the dummy variable for that. If this defect was to be 0, I would have still a measured valued solution, and I would still need to prove that I can identify my measure with the deltas in order to say that this is a weak solution, that I have probability 1 of encountering the solution where it should be. All right. So the third weak formulation is the weak formulation of the energy inequality. And so it's associated with this natural energy structure that I mentioned to you in one of my first slides when I introduced the system itself. And here I have 2 different defects. They are denoted by letter D and DR. So this defect comes from the energy. So energy is the sum of two nonlinear functions of the dummy variables, and hence there is this part. The other defect, this one here, it comes from the fact that we have also some fluxes in the energy equation. So there is a term that depends quadratically on the gradient of the function of the density. Okay, so there is this term, and then there is a term that doesn't end up in the energy, but needs, if you want to perform the energy estimate, this term has to be taken care of, and it needs to be in particular estimated by the energy, which is possible. That's why we have a priori estimates. But what I want to say is that these defects are compatible in the sense that if I show that the defect coming from the energy is equal to 0, then both other defects due to fluxes and due to the advective terms in the momentum equation are identically equal to 0. And that's a very important observation that we used together with Piotr Gwiazda and Nilasis Chanduri to show that, well, the first result is that the measured valued solutions, in the sense that I explained to you before, exist globally in time. But this is very weak solution, you agree with me. It's weaker than the weak solution. I only, instead of having a solution, I have some kind of probability of finding a solution in certain point. But what I do next, and how I actually justify that it makes sense to talk about those solutions, is that if perchance, and I already say it honestly, I don't know anything about strong solutions to this system yet, but if perchance I have a strong solution, let's denote it rho bar, W bar, that will emanate from some initial data in C2. So all of that is on d-dimensional torus. I'm sorry, I forgot to mention it. If I have such strong solution, such that the density, initial density is bounded away from 0, so it's strictly positive function, and the solution is strictly positive as well, so that's the regularity of my solution, then I can say that my Young measure, initial Young measure, the data is a product of deltas really. So in fact, I identify the initial condition pointwisely, and so is the solution itself. So this writing here tells me that my Young measure, my very, very weak solution, measured value solution to the dissipative Aw-Rascle system is in fact centered, is a delta measure centered on the functions which are combinations of the strong of rho bar, W bar, which are strong solution to my system. So this is the so-called weak or measured valued strong uniqueness principle, a sort of equivalent of Prodi-Serene conditions for incompressible Navier-Stokes equations, saying that if I have a solution locally in time with some regularity like this, my weak solution necessarily has to coincide with the strong solution, at least on the lifespan of the strong solution. Well, this is of course very nice, and the positive result, of course, for us. But the next result that I want to present is that this dissipative Aw-Rascle system has actually infinitely many weak solutions. And the result is actually presented in one of the preprints available on arXiv already. And here we were able to extend a little bit the model. So it really doesn't matter that much what the precise form of the offset function is for this result. So therefore, we took a combination of these two approaches, offset function to be sum of the two, a vector of some scalar functions and the gradient of some scalar function, P of rho. Both of these functions, or all entries of this function and gradient of P of rho, can be some singular functions of the density, so something that blows up close to the maximum density constraint. But all the results, the ill-posedness result, will be considered on the d-dimensional torus. Some other domains are also possible and some boundary conditions, but I'm not going to talk about that. The result says basically the following thing. For my Aw-Rascle, dissipative Aw-Rascle system, I can come with any pair of initial condition, rho 0, u0, and any terminal state that I denote by rho t, ut, such that there are some conditions satisfied. So these are all like nice and physical conditions saying, okay, density has to be positive, which is not bad. There is some regularity of the initial and terminal condition. There is conservation, still conservation of mass satisfied by these two states, and actually conservation of the linear momentum. And for any such two states satisfying these physical assumptions, I can build a weak solution that will connect them. So it's not only ill-posedness result, it's like, this is a result that says I can do whatever I want with the system. I can start from zero initial condition and maybe do something crazy, compactly supported in time behavior from 0 to some time t, and I still call this process a weak solution. This is the so-called wild weak solution, and in fact, the proof that we done together with Nilasis Chandouri again and Edward Feyreisel uses the technique of convex integration of Székely and Delelis. So this is the result. It's written for offset functions on 0 infinity, but as I said, we can extend this result to functions defined on the intervals only. And the solutions are weak solutions with this sort of regularity. So density is C2 and velocity is L infinity function. But there is one serious drawback to this weak solutions. These solutions are not physical ones, in a sense that we don't know anything here about energy conservation or energy jumps. We don't even know in which sense the energy inequality would be satisfied. And that's something that we can also remedy to. We can actually improve this result slightly and say that we can build, well, maybe not connect any two states by a weak solution, but we can come up with such initial data, and there will be still infinitely many of them, so that the natural energy, so energy associated with U and the offset function. So this is something that is written in the explicit form, but in fact, it is our old energy rho times W to power 2, if we write offset explicitly. So we can come up with the set of initial data for which the energy inequality is satisfied in the weak sense. So this is an inequality satisfied in the sense of distributions, but we also guarantee that there is no initial energy jump. So whatever we have initially, the energy evolves in such a way that it only may decrease with time. And so this is our final result. And the result says, well, I come up with density. And for this density that satisfies some assumptions, I can choose the initial velocity in this class so that there are still infinitely many weak solutions satisfying the weak formulation of the energy balance. And now I think I have 2 minutes left, or can I bargain and say it's 7 minutes, Trevor?
I'm sure that that's totally fine.
Okay, so I wanted to, so this is some list of references for the method that we use, convex integration technique. But I also wanted to mention our last result and the second part of the topic that I specified for our talk today is the asymptotic analysis of the dissipative Aw-Rascle model in one-dimensional case. So as you maybe recall from one of the first slides, the purpose of all this business was not only to consider Aw-Rascle system to prove existence or disprove well-posedness of the system, but really to study this asymptotic limit epsilon going to 0 in the offset function, right? So we want to take some singular functions. Here the singularity is centered at 1, so rho star is equal to 1. And we want to study the asymptotic limit when this effect of interactions is quite abrupt. So the limit in this Aw-Rascle system when epsilon goes to 0. And before there is a wave of criticism about this model not being suitable for modeling traffic, I would like to maybe mention to you that this model can be used in many other contexts. One of the famous ones is to model the adhesion of the sphere, so through some lubrication forces. Actually, it was postulated by Lefebvre-Lepot and Maury in their paper from 2011, what the limiting system of such limiting procedure leads to when epsilon goes to 0. And this system, the limiting system, is really used to describe the granular media flow. What we did together with my colleagues from France and Nilasis Chandouri was to prove the derivation of such limiting system. I still haven't revealed what the limiting system is, but to prove rigorously that it can be actually obtained through this sort of soft congestion limit when epsilon goes to 0. And to do this, it took us a couple of years, actually. My collaboration with one of the members from my team nowadays, Charlotte Perrin, dates to 2015. And this is when we actually started to use the so-called two-phase compressible, incompressible model to describe the propagation of crowds in big populations. So together with Charlotte Perrin and a couple of co-authors, we were interested in a little bit different model, the two-phase compressible, incompressible Euler system, so to say, that combines the two regimes of some sort of free flow when density is between 0 and strictly below rho star, with the congested flow when density is actually equal to rho star. So this system, it combines effects of compressible and incompressible flow, and it switches from one system to another through this relation. And this relation tells us that if rho is strictly less than rho star, this term is positive, and pi is equal to 0. So a pi which is an unknown, like a pressure in incompressible Euler or Navier-Stokes equations. If, on the other hand, density is equal to rho star, this term is equal to 0, and we actually have incompressible Euler systems, incompressible Euler system, because rho is given, rho star, and the continuity equation reduces to some sort of solenoidal constraint for the velocity vector field. So together with Charlotte, we were able to show that such two-phase system can be approximated by purely compressible system with this unknown pressure, this measure, approximating by some singular function of the density. A little bit like our singular approximation in the offset function in the Aw-Rascle system. So I will not have time to do it here. Let me only tell you that in justifying the asymptotic limit of our Aw-Rascle system, we are not able to use the same arguments that we used 7 years ago, because the system is pressureless and because the singularity now appears in the transport equation. In the transport equation, this is equation written in terms of W. So in the terms of this kind of effective velocity, which is now a sum of the velocity plus some offset function, right? Now, what is a benefit of Aw-Rascle system, why we can actually even think about performing this limit, is an observation that was actually quite a revelation for me, coming from the background of fluids, is that for pressureless system, we not only lose something by not having a priori estimates coming from the pressure term, we actually gain some structure, some nice structure of conservation law, which is not a system of hyperbolic conservation laws, but nevertheless, I can talk about renormalized or entropic solutions to such two conservation laws. And using this kind of entropy structure, we justify the limit passage in both of the equations of the Aw-Rascle system in the weaker sense. It's not as weak sense as the measured valid sense. So these are not Young measures. There still can be some measures, but at least on the torus, we can immediately identify the measures with a weak solution. I'm not going to present you two following slides. There is some notion of duality solutions involved in the limit passage. The duality solutions of Bouchou and Jams that actually allows us to pass to the limit in the troublemaker, the convective term, and to recover the switching relation, which tells us when the system changes from sort of compressible to the incompressible case. All right, so I think I used my extra 5 minutes, and I'm happy to answer any questions or take any comments right now. Thank you for your attention.